So the area of a cross-section doesn't necessarily have to be some sort of predictable or, basic geometric shape. It could be something a little bit more involved. In this particular example, we've got an oil spill that has a particular shape on the surface of the water, right? The region R, which is bounded by the curves sine of x and negative sine of x minus pi over 6. So this region right here is the base of our shape. And then we've got cross sections that are going to be taken perpendicular to the x-axis, which is good news because we don't want to solve those equations for x in terms of y. That would get a little hairy with the inverse sine and the domain restrictions involved. So we're happy with that. So we'll have these cross sections that are dx, and the height here, the side length of these, s of x, is just going to be the top minus the bottom. So s of x is going to be the top function, which is f, minus the bottom function, which is g. Okay? The other part of this is that we have to figure out how big each of those cross-sectional areas is. So it looks like the depth, d, of each cross-section is given by a different function, but it's depending on x. So regardless of whether we're down here on this part of the rectangle, in the middle of the rectangle, or anywhere along this rectangle all the way up to the top, the depth at this particular x value is going to be a constant. So we actually have cross-sections that are rectangles whose base is x and whose height or depth is d. So the area function is going to be found by taking s of x times d of x. Okay? And then we will try to integrate that. We will try to integrate that from this x value to this x value. So this is my x equals a, and this is x equals b. So we're going to try to integrate, to find the volume, we'll integrate from a to b of s of x times d of x dx. Now this is something you probably would not want to try to do by hand. So good news, we notice that it says calculator right here, so this will be a great opportunity for us to play around with a calculator and figure out how to use that to find all the different values. So whenever it says use a calculator, then definitely use a calculator and try not to do anything by hand. So let's see how that's going to work. We're going to use a TI Inspire because I happen to have the emulator for that particular software, but any graphing calculator of your choice will do. So I like to use the scratch pad on here. So hit the home button and click on B to get the graph. And I'm going to go ahead and graph f of x. That was sine of x. So sine of x is f of x. My calculator knows it as f1 of x, but on our paper we know it as f of x. Hit tab for the next one. I'm going to do f2 of x. That's going to be my g of x value of negative sine of x minus pi over 6, x minus pi over 6. And we can see the region that we're interested in is this region over here, right? So a couple things we're going to need. We're going to need to know those points of intersection. So when in doubt, hit menu and see what sort of options we have. We're going to analyze the graph. We're going to find the intersection points. And our lower bound might be 0. Our upper bound might be 1. And we find a point of intersection. That's this point right here, and it is this highlighted area right here, which I will right click on by doing control menu. I'm going to store that, option 4, as A. I'm going to store it as A because that's the first bound of our integral, right? That's the lower x value of our integral. Notice that now that 0.26 is bold, it is now saved. So I'm going to do the same thing again to find B. I'm going to analyze the graph. I'm going to find the intersection point. And I know that it's between it's between 3 and 4. So I'll hit 3, enter, 4, enter. That's going to give us the second point of intersection. So I will control menu to right click on that. I'll store that as B. Oops, that didn't work. Let's try that again. Escape out of that. And make sure that I'm highlighting just that and control menu, store. Let's see if I can, there we go. Escape out of that one more time. Sometimes this is not the easiest tool to use, so we'll try it again. I'm going to try to drag this, oh goodness. If anyone from TI is watching, fix your trackpads, please. They're just terrible. Okay, I'm giving up on that. I'm going to drag it over to here. And I'm just going to use my mouse and right-click on that and store. I'm going to save that as B. All right, great. So now we've got our two values that we're going to need for integration purposes stored in our calculator. And we also have our top minus bottom stored in our calculator. So I'm going to hit the flying calculator button, go back to our calculator side of things, and we're doing calculus, so menu calculus, and we're going to actually do a numerical integral. So numerical integral is option 2 here. We're going to integrate from A to B of our height function, or our side, I'll call it our S of x that we called it on the previous page. That's going to be f of x minus g of x. So in my calculator, I know that as f1 of x, that's f of x, minus g of x, that's known as f2 of x. That is s of x, right? That is the top minus bottom. That's one of our two dimensions. We're going to multiply that by our depth function, d of x. D of x was 2 times the cosine of x over 2. And we'll integrate that with respect to x. Before I hit enter, I always like to double check this, make sure you're in radians mode. Always radians mode with calculus, otherwise things get funky. And that will give us our answer of 4.43511. 4.43511. 4.43511. I'm just double checking, do we know any units here? They don't give us any units, so whatever the units are, it's that thing cubed, right? So if these are measured in feet, then this would be cubic feet, for example. And as far as I can tell, that's all we need to do in this problem. Notice that we don't need to actually show any of that work that we did in the calculator. We might want to say A is approximately equal to and B is approximately equal to, and pull those values out of the calculator, but I'm not sure if we even need to do that as long as we label what A and B are on the graph. But for the sake of completion here, I'll go ahead and put those here. Well, you get the idea. Maybe I'll rewrite that here. A is approximately that, and B is approximately that. And we find those by finding the points of intersection using a calculator. There's no analytic method that I would like to try to do to find those points of intersection. It might be possible, but this is a calculator problem, and we have better things to do with our time. All right, so we'll try one more FRQ type example here. This time, we've got some nice lines to deal with. Y equals 5x, going through the origin with a slope of 5. Then a slope of negative 1/5 with a y-intercept of 3. So this is y equals negative x over 5 plus 3. This is y equals 5x. The line y equals 0 is the x-axis. So we've got this triangular shape that represents our base. And our cross sections are perpendicular to the y-axis this time. That's a new one. So S of x is going to be in terms of y. So this is a dy value, and S of y is going to equal right minus left. These are going to be x values in terms of y. The right value in terms of y will be y minus 3 times negative 5. That's equal to x. That's from this equation right here. So that's going to be negative 5 times y minus 3. And then the left value is going to be x equals 1/5 y, so minus 1/5 y. So that's our x, or our s value. And then, look at that. We don't even need to find that. I didn't even read the question. It's giving us the area function. Mr. Pomerantz needs to read before he jumps into the problem. So we don't even need this. Don't need. I was expecting a geometric problem like maybe this is the side length of a square, for example. But we don't have to do that because they've actually given us whatever the shape is. It doesn't matter. We know what the area is. The only thing we need to do is integrate this from, well, this is in terms of y. So we're starting with a y value of 0 going up to a y value of, I don't know. We're going to have to figure that out. So we can set these two things equal to each other to solve for y. Might as well do that since I've already gone through the process. 1/5 y equals negative 5 y minus 3, or negative 5 y plus 15 equals 1/5 y, or 26 over 5 y equals 15, or y equals 15 times 5 over 26, or 75 over 26. That's the y value of that point right there. This is some x value, comma, 75 over 26. So if I did that correctly, it makes sense, right? That's a little bit bigger than 3, I think. Let me double check that. Flying by the seat of my pants here. Oh, no, it's a little bit less than, oh, no, that's good. It's a little bit less than 3, which is good because we went down a little bit. All right, cool. So that means we're just going to integrate our area function. Nothing to multiply that by because it's already the area. Area times the thickness is going to give us the volume. Yeah, I think we can do this one. Why not? We'll take the antiderivative, 1/3 y cubed plus y, and then evaluate that at 75 over 26. Evaluate that at 0. I like evaluating it at 0 because we don't need to worry about it. So we just have 1/3 of 75 over 26 cubed plus 75 over 26. And I'm going to call that my final answer because I don't feel like working that out. It doesn't say it's a calculator question, so I'm not going to use a calculator, but it also doesn't say simplify your final answer. This is my final answer. It's just not in simplified form, and that's perfectly acceptable. So that would be the volume of the solid. We don't know what that solid looks like. We just know what the areas of the cross sections are. So that's an interesting little twist.